This problem is very similar to one of the problems presented in one of my videos. I have a frame loaded by wind load, which has a trapezoidal shape. My task is to determine forces acting on the left pole, and I would like to present my answers in the form of a free body diagram for that pole. I begin with drawing a free body diagram. I want to pay your attention that I do not immediately convert the trapezoidal load into concentrated forces. Rather, I draw a free body diagram, write down equilibrium equations, and as I need to write down equilibrium equations, I do the conversion. This conversion starts with decomposing the trapezoidal load into a triangular and a rectangular. And then for the triangular load, the replacement involves the force 3AW, which is the area of this triangle, applied at a point located at the distance 2A from the top, 4A from the bottom. For the rectangle, again, the area of the rectangle, 6AW, the force is placed in the middle. Therefore, the original free body diagram is replaced with the one shown here, and I can write down force and moment equilibrium equations to determine the reactions at A and B, and the answers are shown here. And now let me redraw this by showing the actual forces acting on the free frame. In this diagram, I show the connecting bars in green. And the reason I show them in green is to indicate that these bars are two force members, simply because none of them is loaded anywhere in the middle, and all of them are connected to the rest of the frame at the endpoints. This significantly simplifies my task. To proceed further, I will introduce the angle theta, and of course, tangent theta is equal to 1/4. Next, I would like to consider the free body diagram for the pole of interest, and here I show the forces 3AW and 6AW because I know that that's what will happen with the replacement once I write equilibrium equations, and the equilibrium equations are written down here. In this case, I choose the point C for the moment equilibrium equations simply because it eliminates the forces F1 and F2 from that equation, and the moment equilibrium gives me the force F3. Once I solve these equations, I obtain the following answers for the forces F1, F2, and F3, and I would like to pay your attention that at the point C, we have forces F1 and F2 applied together, and it is reasonable to replace these forces with their horizontal and vertical resultants. So to this end, I will rewrite the force F1 in terms of its x and y components. I will do the same for the force F2. The force F2, of course, has only x component. Now, if I add these forces together, I obtained that the resultant force has a horizontal projection of 10 AW and the vertical projection of 7.5 AW, and therefore I can replace the forces acting at C by these two horizontal forces. This allows me to summarize the answer in the following form. Please pay attention that my final answer involves a distributed load rather than concentrated forces replacing that load. The reason it's very important here is the following. Imagine that somebody wants to determine internal forces in this pole once external forces have been determined. The internal forces associated with this actual load are different from those induced by concentrated forces statically equivalent to this load. At any rate, that's the answer to the first problem.